I'm going to introduce Professor Jaikumar Radhakrishnan, who is one of India's leading computer scientists, also one of the best researchers from TIFR. He specializes in combinatorics and communication complexity. He is served as the Dean of the School of Technology and Computer Science at TIFR. He was also awarded the Shanti Swarup Bhatnagar Award in the category of mathematical sciences back in 2008. This is, of course, India's highest honor for excellence in science, mathematics, and technology. He's also a fellow of the Indian Academy of Sciences all the way back from 2007. He's, of course, known for his breadth of knowledge across theory areas. His primary research interests include randomness, computing, quantum information and computation, information theory, and combinatorics. This talk would be on set membership using classical and quantum probes. I hope you enjoy the talk, and without further ado, let me hand it to our speaker.
Thank you very much, Rahul, for the introduction. And, thank you, everybody, for the invitation. I'm going to talk about an old problem. Been looking at it for almost 20 years now, with little progress here and there. So today I'm calling the talk Set Membership with two classical and quantum probes. There are versions of this work where the 2 is replaced by a t, where t is some larger number. But the main results today will be for t equals 2. So since it's an old topic, I have worked on it with various people who are unmentioned on this slide. But there's been some recent progress with Shyam, Dhamapurkar, and Shubham, Pawar. And a good part of today's talk will be work that was done jointly. Good. So what's the problem? The problem is an old data structure problem. So you have to store a set in memory and then answer membership queries. Okay. That's the problem. So M is the size of the universe. So assume M is some large number, and a small set of size n has been identified. And now you want to take this set S and write it as a bit string. Yeah. Sorry? This should have been an M. Okay. Yeah. So this should have been an M, and this is N. Okay. So M is the size of the universe. N is the size of the set. So, and this set is small, and you want to represent this set as a data structure. What's a data structure? It's just a sequence of bits. And then you'll a query, yeah, like everything is wrong. That's why. So this should have been an S. Yeah, X belongs to S. I don't know what I did. So anyway, so you want to represent S. Represent S in memory so that one can determine, given an arbitrary element X, if X belongs to this set of. And you're allowed to look into your data structure and make a few probes. The style of today's discussion will be more information theoretic. That is, we'll actually ask how many bits you have to read from the memory. Okay, so this probably is not terribly practical sort of discussion, because in our memory, things are stored in words, and in each axis, we get all the bits of the word. But I would like to know how many bits we need to read. And so the question is the following. Okay, so let us just look at two classical examples of this problem. So suppose you can store the set S as a characteristic vector. That means your set may be whatever, but you will store m bits, yeah, 0 and 1, If the element is there, you write a 1. If the element is not there in the set, you write a 0. Then, if you're given a particular element I, you can just go into the particular location in this bit string and give the answer. You need just one probe. But the space you need is n bits. The other thing which we are taught is sorted array. I mean, we think of it as you take this set S and you sort it and write it as a table, and then you do binary search to find whether your element is there or not. But if you really break it down into bits, how much do you need? Well, you need, so each element, presumably you'll need log m bits to represent it. So the total amount of space to store the n elements of the set will be like n log m. And to do a query, you will need log n steps of binary search. But each step of binary search, you are reading the entire word. So if you are like really being like a fundamentalist, then you are reading these many bits. So these are two extreme examples. Here you can do it just with one bit, and here you take a lot of bits, but it looks like your space is optimal, because if you want to store a set of size n out of a universe of size n, there are m choose n different sets, and if you take the log of that number, unless n is very large, you get something like n log n. So you have compressed. So you can think of a set of size n as a very sparse vector. Characteristic vector had only n ones initially, and you are asked to compress it and represent it in memory as a bit string. But you also want the ability to decode it quickly. That is, just by looking at a few bits, you should be able to tell whether a particular bit of the original characteristic vector is 0 or 1. This solution says, I won't compress at all. And this solution says, I'll compress like crazy. So
there is an aspect of computation after reading the two bits.
yes. So we are not. So there are two computations which I'm hiding in this, especially in this definition which I described. So one is, given the set, how much effort does it need? Does it take to produce that bit string? You think and think about the set and then come up with this magic string. Yeah, so that is one computation effort. The other is, after reading those bits, how do you assemble? I mean, what computation do you perform on those bits in order to give the final answer? The examples on our discussion today will be in situations where the number of probes you make is just a constant, a small number of probes, yeah, most of the time 2. So that computation will never be very expensive. But the question about how to compress the set, yeah, that question will be unanswered. We'll just say that in principle there is a method to do it. Yeah. So let me just introduce a notation. There is this S, M, N, T. So S, this M is the size of the universe. N is the size of the set. T is the number of probes. And this S in front, yeah, is the amount of space, the best compression you can do. So you've been given a set of size n out of a universe of size n. Compress it. What is the minimum? Yeah, the best compression you can achieve, so that you can answer membership queries using T bit probes. So T is the number of probes. No errors allowed, no randomization, everything is determined. Question? That's right. So you're given an X, the query element. So that is also a valid question. So given the query element, which locations to probe? Okay, might require some computation. All that I'm not talking about. There is in principle an algorithm which, based on the X, will determine which bits to probe adaptively. That is, if you see a 0 in the first probe, you might decide to probe a particular bit. If you see a 1, you might decide to probe some other bit. That's all allowed, but yeah, it depends on X. Now, in this notation, if you try to write down what we discussed before. We know that with one bit of one probe, you can do the characteristic vector, which takes at most m bits. And on the other hand, if you allow yourself so many bits, so many probes, then you can do it in. Again, this is wrong. This is just n log n. Okay. I don't know why I wrote the log n. Yes, sorry. Yeah, I was very confident. Yeah. Okay, so so after the talk, I'll correct all this and you can post it somewhere. Yeah. So we will discuss lower bounds and upper bounds. Upper bounds meaning data structure schemes which solve the problem, and lower bounds means statements like you will need at least this much space. So let me start with an old lower bound, 20 years old. And the main attraction of this is that I'm going to present this lower bound using what's called the polynomial method. Okay. And for some of you, I'm hoping you've not seen algebra being thrown into a problem like this and discussions about polynomials. And I think this, to me, this still is one of the compelling applications of the polynomial method. So let me try and explain. So what is it? We want to prove something like this. The main n is a small number. The thing that you should remember is that as t increases, the space required seems to go as m to the 1 over t. Yeah. And we would like to prove that you will need at least this much. And how does that work? So let's fix a particular scheme for this problem that uses s bits of storage, and we wish to show that s is large. This large. Now, how do we prove this? So let us try to understand what does it mean? What does a scheme mean? So when a particular element x is given, there is a particular strategy that the algorithm has for probing the memory. And let me write down that strategy as a tree. It says I'm going to first probe bit 5. This is just an example. Yeah. And if it is 0, I will probe bit 2. If it is 1, I'll probe bit 1. It will do this for t steps. So the depth of this tree is t. And in the end, based on the answers I have received so far, I'm going to declare the answer yes or no. So any scheme, for each element x, it will have a tree. Yeah? For each element x, a different strategy for deciding whether that element is there or not by probing the memory. The names of the bits of the memory are mentioned here. Only a small number of bits might appear here. Other bits are neglected for a particular x. Maybe they are relevant for some other x. So whenever you have such a decision tree, you can write down a polynomial for it. And what we will do is that we will take these polynomials, one for each x, and combine them and produce polynomials for one for each set. For each set of size n, we will associate a polynomial of small degree. And why would its degree be small? Because the depth of this tree is small. Okay. So the fact that this depth is small will ensure that the polynomial has small degree. And we will argue that these polynomials, yeah, they will have degree at most np, and they are linearly independent as polynomials. These are polynomials of small degree, and they are linearly independent as polynomials. But how many monomials do we have of degree np? At most these many. But how many sets do we have? These. So all these polynomials live in a space of this dimension, and they are linearly independent. So the dimension must be at least as much as the number of sets, and we will be able to write this inequality. And if you kind of play around with this inequality, you get this. So that playing around, I'm not going to describe. Okay, but in the end, we should be able to write this inequality is the question. And why is this? It will somehow come from considerations of these. These will be polynomials in s variables, yeah, and that is why I'm writing S plus NT. Yeah. Actually, yeah. So if you have polynomials in S variables, and we will only require zeros and ones to be substituted into that polynomial, so we can even assume that they are multilinear. So the number of monomials we have is monomials of degree 0, which is a constant, or monomials of degree 1, degree 2, up till NT. So I should actually have written S choose 0 plus S choose 1 plus S choose 2 up till S choose NT, but it's bounded by this number, so I've been lazy. Good. So the strategy is clear. I have not yet told you the one. So write this, put this slide, but maybe I will just say things. People in the room, I should just, maybe you can read the slides, but here's what happens. When we have a decision tree and particular yes appears here, we will think of yes as one value. Yeah. And suppose you went down the tree this bit by probing bit 5, then bit 7. But when you took bit 5, you took the 0 branch of it. When you took bit 7, you took the 1 branch of it, and so on, and you arrived at this particular. Then you can write down a polynomial which will be true only if this part will be taken, and that polynomial will be 1 minus b5. Maybe you are used to b5 complement, but since I'm doing polynomials, I'm writing it as 1 minus b5, then b7, and maybe the next probe was b42, but I went right, and then in b53 I went left, and so on, and then I reach this. So I get one such term. This is how we are taught to produce Boolean formulas from truth tables. Okay. It's the same idea. Yeah. So for each part, each leaf here which has a 1, there is a path. For each part, you build this monomial and add them up. When we get a polynomial in these variables B, how many such variables are there? S of them. So this is a polynomial of degree at most. So that is what I've said. For each path, you have a polynomial, not exactly a monomial, because you probably need to open these out, but you have such a product, and you add them up, and in the end, you get a polynomial. Now, what is the property of this polynomial? If you put an assignment to the values b1 to bx, this is the assignment to your memory, yeah, and you compute this polynomial, when will it come out 1? Precisely when we made this probe for the query x, the answer was yes. Getting an answer yes for this tree is the same as getting the answer 1 for this polynomial. Otherwise, this will give a value 0. This always evaluates. If you are put zeros and ones for the b's, this will always evaluate to 0 or 1, and it will evaluate to 1 exactly when. But this is just, I've shown you how to build a polynomial for an element x. This tree was designed for x. Now, how do you construct a polynomial for a set? Take every element in the set. Yeah, maybe I should have called this x. For every element x in the set, you build its polynomial as you did here, and just multiply it. That is a polynomial for the set, which is what I said we will do. For each set S, we have to build a polynomial. We build it for the individual elements, and we multiply them. Now, the claim is that these polynomials are actually linearly independent. So let us just do that. I should have also checked that there is an eraser. So we have built polynomials for each set. Yes. And suppose there is a linear dependency among these polynomials. This S is, these are sets which are subsets of M, and let's say N size subsets, and we build these polynomials, and suppose this came out to be. And what we want to show that each alpha must be zero. That is what it means for some polynomials to be linearly independent. The only way you can get zero is to take the zero linear. Here's the magic. So look at this particular S, let's say S hat. You go back to the data structure and say, I want to store S hat. So data structure says, okay, here's the bit string. Substitute that bit string. Now, each element in S is going to answer yes on that bit string because that element is in. So this particular polynomial corresponding to S hat will evaluate to 1. For every other set, there is one element of the set, every other S prime, which is not in S, because these are all sets of size N. Yeah. So they will all evaluate to 0. That means alpha S hat is 0, and you could have done this argument for every S hat. So it's clear? Yeah. So build a polynomial for each set. All that looked like, it wasn't clear where we were going, but the killer step is at the end. If you have a particular set, you ask to store it, and now bring the data structure in and say, how are you going to store this set? It says, oh, I'm going to put this value for bit 1 in the data structure, this value, substitute that, and out will pop the conclusion that alpha S hat. So I'll leave it at this. Yeah. As polynomial method arguments in combinatorics go, this is a very baby argument, but yeah, you want to remember how polynomial method, at least the basic polynomial method works. This is a good example. Questions? All right. So this is the this was over here, so this would be over at 2 also. In which case, I would probably have gone through an extra step of making the things multilinear. Yeah. Because whenever it's bi to the power 5 and bi are the same if bi is going to be only zeros and ones. And in the end, in our argument, we are only going to be substituting zeros and ones. So I think that is why I wrote this as the total number of monomials, but ignore everything. Just there's a dimension argument and based on that. Question?
Sorry if I'm asking something that you already said, but why does the polynomial give 0 for some element in some other set?
That's so here was the set S, and here was your set S. And there was a polynomial built for this set S, and that was called P sub S. And how was this polynomial itself built? It was built, suppose S, this set was, it had n elements, and let us call them alpha 1, alpha 2, alpha. So alpha 1 of B1 to BS, P of alpha 2 of B1 to BS, and P of alpha n of. This is what this polynomial is. There is an element y here, which is not in this set. These are two different sets. So what did I say? There's an element y here, which is not in this. So I should. Yes. Sorry, I'm getting all confused right now. So what do I want to do? That for every other set, the answer should be 0. Yes.
So this is PS, right?
But
This is PS.
this is PS.
I think for y, if P subscript y, this would evaluate to 0 because the data structure has to correctly answer if y is not in X. So the tree it evaluates to 0.
One of the element is 0 spectral.
Then the product overall is.
So if I take the element y here and look at the term here for y, p of y, p1 to bx. This represents the tree, the action of the tree for y. Then this is the data in the memory. This is the data that is entered into the memory for the set S hat. So when the query for y is made for the set S hat, the answer is supposed to be 0. So this particular polynomial, which is a factor in PS, is going to evaluate to 0. The others can do what they want. That is going to kill the term.
So B1 to B S is actually the input for S hat.
S hat. Yeah. So that's what confused me also. So the input for S hat is being just so perversely being fit, substituted into the polynomial built for S. But nevertheless, there is each of these factors has to do its own job, and it will give us. Questions?
So here each of these P alpha I, they also have a superscript S, right? This is a polynomial.
No, the polynomial comes. Thank you. The polynomial comes from the tree, and the tree is there once and for all. For each element, for So for each element, there is a strategy. Strategy cannot depend on the set because then, it's not a data structure. Each element has a strategy, and then the only way it gets to know of the set S is through the memory. So the strategy is independent of the set. This tree has no S. This tree for X. Sorry, is it okay? Yeah.
Maybe I'm jumping the gun here, but if you had other additional properties about this is for all size and subsets.
Yes.
It is like, let me just put a concrete example. Let's say you only had to store sub bases of a matroid, which were not
special
all,
sets.
Yeah, special sets. So maybe the degree of the polynomial
Could be smaller. Yeah. And usually, usually the data structure problem when S, M, and T is when you are supposed to store sets of size at most n, not sets of size exactly n. Yeah. Then you can do a little bit here. M choose 0 plus M choose 1 plus M choose n. Get a little bit more out of this. Yeah. How this argument will then work, I will let you think about it. Okay. So let me go on.
It's kind of interesting that this final expression has a form which, if you just showed me this, I would start guessing something like folder or showing a bit. It's completely not that.
It's coming out of this equation. Yeah, it is just counting monomials. The first proof of this was actually combinatorial, but later on we wanted to do it for quantum, and it turned out that the combinatorial argument, we didn't even know what it means in quantum. So, but we knew that in quantum, polynomial lower bounds carry over to quantum, so we just rephrased the argument using this technology, and then so the question is, so in particular, when t equals 1, this says that you will need space M. So characteristic vector, you can't beat it, and that is quite intuitively obvious that if you're just going to get an answer by 1 bit, by probing 1 bit, you should not be able to compress at all. Even sets of size 2. But in general, how good is this lower bound? And notice that here the expression 1 over t appears. And yeah, Mohit Garg, who was a PhD student at IISc, Mumbai, he in his thesis showed that yeah, instead of 1 over t, it looks like 2 over t. Okay, and then there is some logarithmic factors. So it may be considered okay. So we sort of understand the problem, not exactly, and so you take t equals 2. Yeah. So this one is an upper. And we will generally be interested in sets which are not too large. They are m to the 1 minus epsilon. Your universe is of size m, square root m, m to the 3/4. Very small sets of that. Now, it can also be shown that when t equals 2 and your probes are non-adaptive, that is, you have to read 2 bits and give the answer, then again, there is no savings possible. It doesn't follow from this lower bound, but even like non-adaptive, even with 2 probes, you will not be able to do better. But with two probes adaptive, what can you do? And so Alone and Feige, they showed, I mean, this is around 2007, yeah, things are really good, that actually some savings over, so I'll try and explain. Yeah. So if you were going to use the characteristic vector, you would need m bits. Okay. Now, suppose your set size n is much smaller than log n, very small set size, set of size 10, 20, square root log n. Then there's a log n in the denominator. This looks like log n, don't worry about it. And this n is less than this log n. So you can do slightly better than, yeah, when sets are very small. You don't need the characteristic vector. But if sets become bigger than log n, it's not n factorial, it's an explanation. So much bigger than log n, then this method is powerless. It doesn't give you anything back. And it may be for any n, but then for n which are bigger, it becomes ridiculous in the sense that it's more than m, and we would rather use the characteristic. So I think that's why they probably, I don't remember, but they probably assume that it is less than log m, otherwise use the characteristic. So the question is, why does, and there is some improvement, why does this improvement go away when sets become log n for 2 probes? And are there other schemes that could do anything better? The lower bound is like m to the 1 over t. So with t equals 2, you should be able to get square root m size data structure. But this is like close to linear, almost linear size data structure is all that they are offering for 2-bit probes. So what Mohit showed in his is that you can get a better lower bound. So not the polynomial method lower bound, a different lower bound, which looks like m to the 1 minus 1 over 4n. Yeah, when you allow only 2 probes. So in particular, when m becomes something like log m, n becomes something like log m, this is m times m to the power something like 1 over log m. M to the 1 over log m is constant. Yeah. So it does say, this lower bound says that failure to give anything substantial after set size log m in the alone Feige example is not because, you know, they missed something. It is inherent. You cannot get better than characteristic vector, better than linear, if allow yourself only 2 bit probes. But if you have sets of very small size, let's say your set is of size 20, then actually you can do much better than this. You can get m to the power 1 minus some constant. But this, the improvement that you get in this constant just sort of vanishes as this n goes towards log n. So basically, you see the form of the lower bound and the upper bound is roughly the same. The constants are in the wrong place. Yeah, but Mohit's work essentially gives us an understanding of what happens with two probes, not precise. Now, after this, for small values of n, there have been like all kinds of work. So if my set has only 3 elements, then this was a general upper bound. And what can you do? You can do m to the 2/3 if you're to store only sets of size at most 3. And if you want to store sets of size at most 4, you get m to the 5/6, which is better than what you will get by putting 4 here anyway. 4 here gives nothing. And so on. So we actually, so now I'll finally talk about the work with Shyam, Dhamapurkar and Shubham, Pawar. And it concerns this function for small values of n. And what we show is we improve the upper bound. Sorry, I should have said an upper bound. So the upper bound, and this should have been a big O here, which I have not written. So like m to the minus 1 over n. In Mohit's upper bound, I don't know what's going on here. Everything seems to be wrong. Sorry, how does this even? Anyway, I'll fix that later, but yeah. So you get a slight savings over the characteristic vector for small sets. If n becomes large, the improvement that you get goes away again. But the improvement here is, I think what has happened is the 4 in the denominator should have been here, and this 4 should have been there. But okay. So, and the lower bound is of the form m to the minus 2 over n. So what I'm going to do today is sort of give you an idea of how you construct schemes for 2-bit probes. Okay, and then I will tell you about a similar scheme with quantum. So since I've been making good progress, for the classical scheme, I just hand wave, and the quantum argument is substantially interesting, and it doesn't need any quantum knowledge. So I'm very keen to discuss that. So in 5 minutes, let me tell you how this particular upper bound gets proved. And so it's something that is based on dense graphs of high girth. That means you have a graph, you want to pack in a lot of edges, but you don't want small cycles. Girth means the size of the smallest cycle. How many edges can you pack into a graph with n vertices without inducing a small cycle? So this is a graph theory problem. It has been studied for 50, 60, 70 years. Yeah. And somehow the existence of graphs constructed in graph theory, which are dense but don't have small cycles, can be leveraged to provide efficient data structure solutions, which will give you bounds like this. That is, and how do you use this? So let me try and explain. Yeah. So here's a dense graph. Our little m, the size of the universe, size of the set will come. But right now, just so I'm giving you a rough scheme of how the data structure is to be built out of a dense graph. So here's a dense graph. Many edges. How many edges? There are capital M edges. And there are n vertices, and m is substantially bigger than n. It's quite a dense graph. And then what we will do is, we will, in our data structure, we will have one bit on each edge. Okay? So several elements will come and probe a particular bit. So each element of our universe will be assigned an edge in this graph. And when we want to query that element, it will come and read this bit. And this bit will direct that element either to this vertex or to this vertex. So this bit says go to V or go to W. And at V and W, there will be these arrays, which there will be a position like the characteristic vector where the answer for that element will be stored. Once again, two probes. First probe, look at the edge. The edge will tell you whether to go left or right. And when you go in that direction, you have made your first probe. You're ready for your second probe. In the array which is located at that vertex, there will be a particular position dedicated to you. You read that. If you see 1, you say, yes, I'm in the set. If you see 0, you say, I'm not in the set. That will be the scheme. Okay. Now, we need to understand what happens to the size. When our number of elements is little m, the number of edges is capital M. So the number of elements that are probing a common edge is like m over n. For each of those elements, I have to keep provision for the second probe. So I need m over m bits in each of these arrays which are located at these vertices. And so the total number of bits is m bits for the first probe and these many bits for the second probe. I mean, and if you understand this, then you understood whatever I was trying to say before. Okay. First probe, m bits, 1 for each edge. Second probe into these arrays. The number of arrays is equal to the number of vertices. Each array has these many elements. So this now, but notice that there is a bit here, and there are some elements which are probing this, and they could well be directed into this same array. So we might say that this array is dedicated to elements which probe this, but the very same array is also dedicated or also kept for elements that probe this edge in their first probe. Now, if there is an element here which is in the set, you would be inclined to write 1 here, but it could be that there is an element which is not in the set, which was sent this way and is reading the same bit and getting a wrong answer. Yeah. It was directed this side because there was some other element which was interested in reading this bit, but all of them come together. And then it turns out that an element from here and an element from there both read the same bit. One of them was actually in the set. The other just happened by accident to read the same bit and declare that it is in the set. This should not happen. That means we need to orient these edges. Yeah. So we have been given this graph, which I call edge, yeah, this graph, and we have some edges. We need to orient the edges carefully so that this sort of mishap does not happen. And it turns out that if this graph has high enough girth compared to the size of the set that you are storing, if the girth is much bigger than the size of the set you are storing, then you can always direct the edges of this graph so that such problems do not occur. It involves a graph theory lemma, which is written here, and it's annoying to prove. Okay, but that is all. After this, go to the literature, find dense graphs of high girth, plug it here, and extract the solution, and you will get results which I mentioned. Good. Yeah. So I'll just leave it at that. You can look at the paper, or you can ask. On questions.
Since it's a very beautifully curated hashing. It says that whenever you have a hash collision, you kind of try to
avoid. Yeah. So the hash function.
Right.
Yeah. So it's a strange thing. That, yeah. So I think the way you are thinking about it is that the first bit, the first probe is telling you what your hash function is, and the second tells you where to go and look. Yeah. But the hash function, usually when we talk about hash function, we look for small representations for hash functions. But this is a hash function which is represented in a distributed way. Some elements, when they want to find out where they are to be hashed, they look here. Some other elements look somewhere else. In standard hashing that we are taught, you first go and read the hash function from the table, which is stored in the first 4 positions in the table, which are some log n bit numbers, and then based on that do further computation. So, but it's fair to think about it like the first probe tells you your hash function, but the element X doesn't need to know where Y is being hashed. So it just reads one bit and determines whether to go here or there, and somehow things have been kept nicely arranged there. Go to quantum, yeah, and I'll explain everything if you. By now everybody knows quantum, but I'll say it the way I understand.
Okay. This is also one funny question. This is in some sense also tight. Like if I were to tell you a lower bound for the set membership data structure, does that translates also to the blur structure?
So it is true that it doesn't immediately. So it is not. It's not so tight that if somebody came with a very good data structure construction, that would immediately improve the current technology in the girth world. But the lower bound, which I didn't present, yeah, does go through considerations of girth. That is, if there is efficient data structure, then if your graph is dense, then there will be short cycles in the graph. And if there are short cycles in the graph, we will be able to argue that the data structure is making an error. Good. So let us just step back a little bit and ask, what is a data structure again? Yeah. So an element X or I is sent. So what is memory? Yeah. Memory, you give it an address and you get a value. That's what an array is. Yeah. Feed an address. If the memory has S bits, then the address comes in log S bits, and you get a value, which is a bit. That is what memory is. In quantum, here's what it happens. You give I, and you also give a bit B. So this is just some sort of a reversible version of this. Yeah. Don't take the word reversible very seriously. So you're given this address to probe this array in, and you are also given this bit B, and the answer you are supposed to provide in this slightly perverse way. The index I, which is stored on some registers, or some wires, some bus, comes out as it is, don't disturb I. The value of A will ride on this register. So if AI was supposed to be 1, then flip this bit B. If AI was supposed to be 0, leave the bit B as it is. So we are allowed, so a data structure in quantum will be an array like this, to which you can feed an index and a value bit B. The index will come out as it is. The bit B will be flipped if AI was 1, and it will stay as it is if AI is. Now, given that this is what memory is, what is a data structure? Well, in classical also you can say, what was a data structure? You were given some query element X, you did some computation, then decided to probe the array once. Some data you kept in your memory as it is, and some data you extracted out of this array. And then you did some more computation. Imagine that this was classical computation, then decided which bit to probe next, and then again looked at the array, and then finally did the final computation in order to extract the answer. And maybe the answer was stored on this wire. Okay. So you can imagine that even your classical computer inside, if you just unraveled the computation as circuit, this is what it would look like. Yeah. There would be an initial computation, an access to the array, in further computation, access to the array, and a final computation and the answer. Okay. In quantum, it's the same. There will be some quantum computation initially. Yeah, instead of the usual ands, ors, and nots, these are some unitary operations. We don't need to know. Okay, and then the circuit will involve reading this bit, and then some further quantum computation will be done. Then it will again read this or send some, state into this circuit. The answer will come according to this rule, and then some final processing will be done. So this is what we mean by a quantum circuit. Now, to know anything, and the reason is that the only fact we will use is that if a quantum algorithm needs to know the XOR of 2 bits in the memory, it can do it with just one probe. This is what is called Deutsch's algorithm. So in classical, suppose somewhere in the data structure or in your code, you said compute the XOR of A7 and A9. You will probe A once to extract A7, probe it again to get A9, and do the XOR ourselves. In quantum, somehow, there is facility for you to send something called a superposition into memory and do some little bit of post-processing, and you will get the XOR of A7 and A9 in one step. So from now on, imagine our data structure will say that we are still doing classical computation. The only extra privilege we will give us is that whenever we need to compute XOR of 2 bits, we can compute it in one step. We will count it as one probe instead of 2 probes. Okay? And we don't need to know anything else about it. So what I'm going to show now is how a data structure works, where if we are allowed in each probe to compute the XOR of 2 bits. And if you could do that, then that implies that there is a quantum algorithm, because XOR of 2 bits can be done with only one probe by quantum. Is this clear? So yes, I think you're relieved, no more quantum. Yes. And what will be our result? Notice that I made this big deal about the fact that with 2 probes, classical schemes, even when sets became log m, there was no improvement possible. And the very fact that you can compute XOR of 2 bits in one probe tells you that even for sets of size m to the 1/8, don't take these numbers very seriously. Even with sets of size m to the 1/8, you can do much better than the characteristic vector. Classically, sets beyond log m, you cannot beat the characteristic vector. Here, even sets which are quite big, m to the 1/8, you can beat the characteristic vector. That is the result. Okay. Questions? And how do we prove it? Again, through graphs. And this time, instead of question. Yes, the lower bound that I mentioned, which came out of the polynomial method, is applicable. That gives you a lower bound of square root m. Even for sets of size 2, you will need at least square root m space. Okay, but the question was, can you do anything better than m? And when sets became larger than log n, we could not. In classical, and probably could not because Mohit gave a lower bound. But here we can beat that. Yeah, and the only thing we need to remember is if you can do XOR queries, XOR of 2 bits at a time, you can already get it. Question. Now, how does this work? Again, largely I will handle it, but I'll give you an. So again, it will be based on graphs. Okay. So here's what. So actually, we will give you. We'll have a 2 probe scheme, but the first probe will actually be classical. We will go and read only 1 bit, no XOR in the first probe, as we did in a classical data set. Based on that 1 bit that we read, we will determine the XOR of which 2 bits we need to compute. Okay. And that we will do in the second bit. The second step, we need quantum because we are trying to compute XOR. The first one is just, so it's the same as before. So there will be a graph. It will be a dense graph, but girth will not be the issue here. Okay, so it will be a dense graph, and on each edge, there will be a bit that is stored. Some elements would like to read this edge, some other elements of the universe would read this edge. They will all be assigned their edges to read. Okay. Once they read this edge, read the bit on this edge, if the bit comes out to be 0, they go into this space. Otherwise, they go into this space. And here, on these two vertices, yeah, there will be arrays, just as before. Yeah, but last time they were reading one of the arrays. They will take a bit of the first array, a bit of the second array on the two vertices and compute their XOR. And that will be the answer. This is the data structure clear. So we will deal with graphs, but there will be a first probe as before on an edge, which will tell you whether to go up or down. And wherever you go, you are going to. And again, let us quickly do a computation to check whether we understand. So how much space did we use? Well, here, how many bits did we store? One for each edge. And here, one at each vertex. And there were these many bits to be stored for each vertex. But there were two such data structures, so there is a factor. The whole point is, now somebody has given us a set S of this size, huge set. Yeah. How are we going to put the bits on these edges and into these arrays so that all queries are answered correctly? That's it. And last time I said somehow high girth does the job. Let us see, yeah, how we are going to do it now. And so I'll take 3 more minutes. Nothing very heavy. So here are 2 bits. They were part of some array. And here is an element X, which needs to compute the XOR of these two to determine its answer. And there was some other element X prime, which was reading this. And some other element which was reading this bit. This bit was a part of some array. Suppose this element is in the set. 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 And this element. Now, you see, if these elements are in the set, the XOR of these two should be 1. The XOR of these two should be 1. XOR of these two should be 1. XOR of these two should be 1. Right? This says this bit plus this bit equals 1 or 2. You sum all these equations, all these intermediate variables will cancel out because they appear twice, once for this equation and this equation. And this becomes dependent on this. Once you know the value of this, you do not have freedom to, so in this case, it is an odd cycle. 1 plus 1 plus 1 plus 1. So if this element is in the set, this element is in the set, this element is in the set, and this element is in the set, if you had such a structure, you would not have freedom to put y in the set. Automatically, you will have a query for y will come out 0. So this is a danger. If such a thing appears, yeah, that is when cycles appear, XORs get into trouble because the XOR of this, XOR of this, XOR of this, and XOR of this determines the XOR of this. So if somebody said store a set where this element, this element, this element, this element are in, and this element is not in, will be in trouble. So in that case, you should send these elements maybe to the top and this element to the bottom, so that they are not reading the same parts of the method. But when can you be sure that you will be able to set all your XORs correctly? If you had this complex web of equations, but there was no cycle, then you can set the bits here so that every XOR comes out exactly what you want. If you have a set of equations with two variables per equation, mod 2, but the underlying graph is a tree, then actually you can always find a solution. Set any of the bits, any one bit to anything, and then everything else gets forced. So this graph here, the initial graph, if somehow it was dense, but we could split it up into two trees. One tree will go up, one tree will go down, and we will do the assignment in both the trees. We'll be happy. And I don't know what's happening. Why is it refusing to move now? Or that also. Good. So let me not say more. There is a theorem of Nash-Williams which says, and I think if you've not seen this is probably the best thing in the talk. Yeah. So if for every subset, so you've been given a graph, you want to know when can you split it up into two trees. If for every subset, the number of edges is less than the number of set of vertices, the number of edges is less than the number of vertices minus 1. If you had it, yeah, 2 times the number of vertices minus 1, it's a necessary condition. Turns out that it is sufficient. Yeah, then such a graph can always be split into two trees. We will make use of this theorem, and how? Don't worry about this calculation. Yeah. So what we will do is we will take this graph, the fact that so it will be a randomly constructed graph with some properties that it is locally sparse. So we have got these elements that we want to store. Those are the green edges. Turns out that if the graph is sparse, then there is a region in which this I call core, where all the interesting edges are kept. There are these bridge edges which connect you to the rest of the graph. This core will be sparse enough that you can apply Nash-Williams theorem. And you split that core into two trees. Then these bridge edges we will add to one of the trees, and these edges in the outer mode, yeah, will be put to the other one, and they will not interfere. And then you can do the assignment for each of them and settle the problem. Okay. So finally, yeah. So what did I tell you? I told you a polynomial method proof of this. I hope, yeah, that was interesting. A classical upper bound, but the classical upper bound used the existence of dense graphs of high girth, which we pick up from the literature. Quantum upper bound, the only property of quantum algorithms we used was the fact that they could do XOR of 2 bits. So you could create a model of computation where XOR of 2 bits can be done in one step, and then that would constitute a 2-bit quantum data structure. And again, this was based on graphs, and we used dense, locally sparse graphs whose construction I did not show you. A probabilistic construction does the job. I believe these heavily expanding graphs whose construction, explicit constructions exist, can also be used for this, but I have not checked it yet. And we used a classical theorem in this case of Nash-Williams to finish. So, any questions? There was a factor 2 in the exponent in Mohit's lower bound and upper bound. I would be very interested. I think this is a fundamental question about the limits of compression. How much can you compress? Can you compress it to the information theoretic optimal and still be able to answer queries? Yeah, up to the lower bound. And it would be interesting for me to know. For quantum, yeah, so the lower bound is still applicable. It could be that the fact that you can do these XORs, it has not been examined very much. What can you do with 2-bit XORs? Okay. So it could be that the lower bound can be met by quantum algorithms immediately. Okay, it's worth examining. Yeah. And this I've been peddling for many years. The smallest problem for which we don't know the answer is if you have a universe of size n, we want to store sets of size 2 and answer queries classically with 2-bit probes. What is this number? We know upper bounds of m to the 2/3 and lower bounds of m to the 4/7. Yeah. And it would, I think basically a graph theoretic analysis is needed here. 2-bit probes always turn out to be like graph theory. I mean, it is like 2-SAT. I mean, you have constraints on some 2 locations. Yeah. So it may be amenable to graph theoretic analysis. Looks a little complicated. So I went over time. I'm very sorry, but that's not.
We'll take questions now. We thank the speaker for his very nice talk, and we'll take a few questions, and then if you wait around, there's lunch.
So, for that argument, was it sufficient to work with graphs that partition into graphs? Maybe we need to decide on the size.
Yeah. So the problem is not enough. I actually have said it the other day. This element, I'm told that this element is not in the set. This element is not in the set. This element is not in the set. And this element is not in the set. That also forces this element to be not in the set. Okay. So, yeah, so the absence of elements also has consequences. It's not just the presence of elements. Even though this was a short cycle, yeah, it could be a very long cycle, but consisting of elements which are declared to be not in the set. And then there's one last element which is to be in the set. And you will get stuck.
How the polynomial method, that argument extends to possible.
Yeah. So whenever you have quantum data structure, yeah, that's quantum data structure, I declared it like this. Yeah. The operation that it's performing is some reversible operation. Yeah. So that corresponds to some, in the classical setting, some sort of permutation. So it turns out that the bits that you have stored here, yeah, you can write variables for them, like we did V1, V2, etc. And then when you multiply these matrices, yeah, everything that comes up in the end becomes polynomial in these variables. You are trying to populate this matrix in a certain way, using some choices of bits, so that a particular wire in the end is carrying your answer. And it should come with probability 1. To ask what is the amplitude that is accumulating here, it will be product of these matrices and a particular entry of that matrix. But if all entries of intermediate matrices are these plain variables, that product will be a polynomial. And again, the number of queries corresponds to the degree, maybe it's small. Sometimes there is a factor 2 that comes in quantum because it's an amplitude and you need to square it to get the probability. But here we are looking at the zero error case, so things are somewhat safer and essentially the same like that. When you did product of several polynomials, you produce the polynomial for a set, the tensor product. So, okay. Not important. If you insist that you will use the polynomial method, essentially there's only one way to do it. Question.
What if we ask for the answer to the set membership question with high probability?
So this is what we did 20 years ago. So if you are allowed randomness, it turns out that you can compress the information theoretic optimum, that n log n, and answer query. Give me any set of size n. I will design a scheme for sets of size n, where sets of size n will be compressed to space n log n, the information. And then, given a query element x, I will randomly probe some bit based on the element x, and whatever is stored there will be my answer. And with high probability, not for most elements, for every element with high probability, my answer will be correct. Might look obviously wrong, but essentially using the Nissan recursive designs. So I'm sorry, I'm like really want to say this sort of thing. It's getting cold. But here's your memory. This time I'm writing it as a box. A particular element x is going to probe one of these bits, and give the answer. Another element y is going to probe. If it turns out that there are any collection of n sets doesn't dominate another set, that doesn't eat up a lot of this, then the sets which are the elements which are in the set, their sets you can make predominantly 1 and still leave the other sets predominantly 0. So when an element x comes, it will go to each set and read one of these bits. Okay. It's predominantly 1, so the answer will be 1. Elements which are not in the set, in the process of making these predominantly 1, we have not destroyed their zeroness. So they will continue. So it comes to construction of these sets with the property that no set is covered by the union of n others. And constructions exist. Constructions can also be obtained out of expanded tasks. So that's the surprising thing, that if you allow randomness, then the problem sort of goes away. You can get optimal compression and optimum number of rows. Yes. Stop. Yeah.
Quantum does not help at all.
Like, what can you do better than 1? There's an epsilon, and there is a dependence on the space for epsilon. Okay. So there might be some nitpicking to be done there. That is, a classical algorithm, its space deteriorates with epsilon at this rate, but the quantum its rate doesn't deteriorate with epsilon. That's something we have to investigate. Other than that, you're achieving everything with one probe.
If no more questions, can I call upon Professor Anand to give a vote of thanks to the
It's okay. I can. Thank you all for coming.
There's a picture.
Oh, and you should wear next week. Okay, next week. Thanks, sir. So we're done. I mean,
Yeah. I guess we can all proceed down to the lawns.
Akshay will come here.
Yeah, so what time will you be able to?
yeah.
2 o'clock. Okay.
I think I have your phone. I'll give you a call.